All right, back from break. We spent a fair amount of time talking about some of the particle accelerators, some of the detectors that are used in some of these experiments. And this chapter does have a different feel to it in that respect. What we're really interested in, well, once again, as I've been saying, I think with all these chapters, is take a look at the homework problems. So to get a feel for the kinds of problems that might show up on a midterm or on a final exam or something, the kind of problem setup and the calculations that you're expected to be able to do from the chapter, take a look at that. So what I would say is, if you can look at this pattern of particles that we have in terms of the leptons and the quarks, and then an understanding of what other kinds of particles can be created from the quarks. And then take a look at the forces that we have listed here. Just having that much background, I think, will enable you to get through the homework problems. A lot of the formulas we're using are actually coming from earlier chapters, and what we're doing is we're applying them to this new list of fundamental particles that we've learned about in this chapter. So let's move on and talk a little bit more. Here is the slide that the textbook has provided, talking about the weak force in terms of the W plus, the W minus, and the neutral Z. Again, these are really high mass particles. They have masses. The W's are like 80 times the mass of a proton. The Z's are like 90 times the mass of a proton. And now we have directly observed these. So again, this is just has been such a successful endeavor in terms of prediction, and then observation, and observation leading to new predictions of what should be out there, and then going back and building new experiments that would enable these additional observations. Okay, what I'd like to do is look at a couple of examples of what are called Feynman diagrams. We did these very briefly back when we were looking at radioactive decay, in particular beta minus decay. In beta minus decay, we said that the underlying reaction was a neutron turning into a proton, and at the same time an electron and an antineutrino were created. Well, now that we've had this discussion in chapter 43 about fundamental particles, now we realize there's a fundamental way of breaking this down. The neutron itself is made out of 3 quarks being held together with lots of gluons. So I can take those quarks, flavors up, down, and down, and say this is what's going into the reaction is the neutron. And then what's coming out of the reaction, or out of the particle decay, would still be those same quarks. But now one of them has changed flavor. And since one of the quarks has changed flavor, we have gone from a down quark to an up quark. Now it turns out that the only force in nature that is able to change the flavor of a quark or a lepton is the weak force. And even within the weak force, it's only the W that can change flavors. And so when this down flavored quark becomes an up flavored quark, we now have a proton. Well, that's charged. The neutron was not charged. What's happened to the electric charge? Well, the W has carried away that negative charge, and then the W will be coupled to this other formation of an electron and a neutrino. Now this needs to be a particle antiparticle, and so in this case it's the electron that's the particle, and it's the anti-electron neutrino that's the antiparticle. So sometimes students ask, well, if it's neutral, how can it have an antiparticle? And it just does. I mean, if we run reactions with a bunch of neutrinos, we don't get the same reactions as if we run those reactions using antineutrinos. So antineutrinos will turn into anti-electrons, for example, but they won't turn into electrons. The antineutrinos here can be coupled with the electron. The electron, which is a particle, would not show up at the same time as a neutrino itself. That would be creating two particles, and we never observe that to be a case. So we can create beams of these particles, of these different types of neutrinos, and when we create beams of neutrinos and we run them at objects, we see that there are some particles that they will turn into, but not others, based on what kind of neutrino they are. So these are distinct particles. All right, so the little squiggly lines here, these are the gluons. Now, the Q value for this particular reaction, I can get by taking the mass of the neutron, the proton, the electron, and the mass of a neutrino, subtracting those, and we get, you can see how low the mass is on the neutrinos, 0.782 MeV. So, and that's what's referred to as a Feynman diagram. Now what happens here is that quarks and leptons are represented by solid continuous lines. These are conserved particles, and so we have to be able to account for every quark and every lepton. 3 quarks went in, that means 3 quarks need to be coming out of that reaction. So 3 net quarks go in, 3 net quarks go out. Now in terms of the leptons, there were no leptons that went into the reaction. Now that still allows for the possibility that I could get a lepton, anti-lepton coming out of the reaction, and that's what we have. So again, I can't produce 2 leptons, because I didn't start with any at all, but we can have a lepton, anti-lepton formed in the reaction, and that's what's happening here. Okay, here's another example of a Feynman diagram. So we're going to start off with, now this is a lepton. If we go back, here's a quick review of, here are all the different flavors of leptons, here are all the flavors of quarks. We're looking at this particle, the muon, which is a heavy version of the electron. Now the muon's not stable. The muon will decay, and when particles decay, they tend to turn into another particle. Well, let's take a look and see. This muon is going to turn into its neutrino. So this muon decays and becomes its neutrino. Now again, we're depending on the W, the weak force, to mediate this reaction. And so the W allows the muon to convert into its neutrino. At the same time, whatever energy differences, whatever momentum differences, whatever spin differences between these particles, the W will carry that away and then be coupled to another reaction. And the other reaction here are the electron and an anti-electron neutrino. The Q value on this reaction, putting in all the masses, here are all the masses listed, would be 105.15. This is an A decays into B, C, D reaction, kind of like the last one, very similar. And so what that says we could do is, let's do this. Since it's decaying into 3 particles, there's not just one way that the energy can be divided up. If you remember, back when we had, like alpha decay, if there are just 2 particles coming out of the decay, then momentum conservation and energy conservation provides enough constraint that we can say exactly how the energy gets divided up between the 2 particles. But if there's 3 or more particles in the decay, there are many ways that that could happen. Now one possibility would be, and this is just one of many different possibilities, let's say the muon is at rest and it decays. We get these 3 particles coming out. Well, what if the electron that is produced also is at rest after the reaction? Well, if the electron is at rest also, then all we're left with are the 2 neutrinos flying out in opposite directions. How will the energy get divided up? And to determine that, what we can do is we can take the mass of the muon, the mass of the electron, we can take the difference between them. So what we're going to do is we're going to say that the mass we have to work with is the difference between the muon and the electron. Now again, the only reason that we get to do that is because the electron is at rest after the reaction has occurred. And then we're going to say M1 and M2 are given by the masses of the two neutrinos. The neutrinos have really, really low masses. We can basically put their masses at 0 and carry out this calculation. Since they have very similar and very low masses, the energy is going to get divided up more or less equally. There's going to be a slight difference because their masses aren't exactly the same, but to a good approximation, the available kinetic energy given by the Q gets divided up equally between those two particles. All right, here's one more, I think, that we can look at. Let's look at a pion decay. If you remember, we had mentioned the pion. Let's look at the pi plus. That's an up quark with an anti-down. Now, up quarks were plus 2/3, downs were minus 1/3, but it's an anti-down. So that would be plus 2/3 plus 1/3. Oh yeah, that would add up to plus 1. So what's kind of interesting here too is that the quarks have these charges of 2/3 and 1/3, but because quarks always come in threes, or they come in quark anti-quark, go try this out. Any combination of quark anti-quark, or any combination of quark quark quark, will end up with an integer value of charge. So the quarks themselves are fractional, 2/3 and 1/3, but the combinations of the quarks always give us something that's neutral, plus 1, plus 2, minus 1. It's always an integer value. So these pions are an example. This is 2/3 and 1/3, and that adds up to 1 full charge on the pion. Now in this case, since the pion consists of a quark anti-quark, they can react. A particle antiparticle can be connected. So the continuous line here would be a line of the up quark coming in, and then we actually, for antiparticles, we draw these in the opposite direction. So we say, in some sense, the up quark and this anti-down, in some sense, they're the same particle. Okay, so they are connected with that solid line. Now, when they react, that leaves us with this W as an intermediate particle, and then that quickly reconnects with the muon, as this is the specific reaction, and the neutrino. So, and this is a particle and an antiparticle. This is a lepton and an anti-lepton. That's coming out of the reaction. Q value, if I look up the numbers on this, the Q value is 33.91. Again, we can use this formula. Now in this case, there are only 2 particles coming out of the reaction. So this is an A decays to B and C, and that says we can use our kinetic energy formulas that we've been using. We used these a lot back in the nuclear radioactive decay part of the chapter, and we actually used them back in relativity also. But what we can do is kind of systematically plug the numbers in to these formulas, find out how the energy, the Q, is going to get divided up. There's 33.9 MeV available. This is how that divides up. And then we can actually go in and use a little more relativity and show how fast the particles are going. Now, if we assume that the neutrino has a mass of about 1 eV, it says that the neutrinos are coming out at 0.999999999999956 times c. So those neutrinos are coming out pretty close to the speed of light because they have such low mass. It doesn't take very much kinetic energy to bring them up to a really, really high speed. Okay, here's another kind of interesting thing that goes on at the level of fundamental particles. let's say this. Let's say that we're going to run a reaction where we have an electron. Now this is an anti-electron. So let's say we have an electron and an anti-electron that react, but they come out as an electron and an anti-electron. So instead of turning into two photons, which we've seen before, in this reaction, they just run into each other, they get redirected, but they come back out. So one of the possible ways that could happen would be for the electron to come in, and then here is the anti-electron coming in. Now this gets to be a little confusing because we've got the arrows backwards to indicate this is a antiparticle. But what these diagrams are designed as is time. I've drawn the diagrams with time going left to right. I'm more familiar with that convention rather than from bottom to top. So here is the electron coming in, here is the anti-electron coming in. In this diagram, they react through the intermediate photon right here, and as a result, they exchange energy and momentum, and that means that they're going to come out in directions different from the directions that they came in. That's an example of one diagram. Now there's what's called an amplitude that we write down for that. So this is kind of reminiscent of what we saw back when we were looking at light. Back in chapters 34 and 35, we were looking at interference effects. What are the different possible paths that the light could take? Well, in particle physics, different paths correspond to different diagrams. So it could be that this electron went in and it came back out. This anti-electron, this positron went in and came back out. That's one possible thing that happened. Well, there's another possibility as to what happened. It could be that the electron and the anti-electron came in and they annihilated right there. And that the photon then took the combined energy and momentum of these particles and ended up creating a new electron-anti-electron pair. So which is it? Which happened in the reaction? Are the electron and the anti-electron coming out the same particles that went in? Or is the electron and the anti-electron coming out, is that a new particle-antiparticle pair that was formed? And quantum mechanics says they both happened. In order to correctly predict the properties of the particles coming out, we have to say that both happened, and we have to use interference calculations. If you remember, back when we were looking at the different possible paths that light had taken, we had to calculate the amplitude along one path, calculate the amplitude along the other path, add those together, and square them to get a probability. It's the same rules here, except that individual paths correspond to individual diagrams about which particles occurred and how the particles were connected. Sounds crazy, but it works. It correctly, accurately predicts what goes on in our experiments, and it accurately predicts these sometimes to, a few parts in a million. These are really, really extraordinarily accurate predictions of what we observe. Now, just to show you what the amplitudes, we are not doing these calculations, but that's what the calculations look like. If you look back to chapter 38, where we introduce the idea of wave functions, what we do is we get a wave function for the particles going in, we get wave functions for the particles coming out, we get wave functions for all of the intermediary particles. We pack them all together inside an integration sign. We integrate over x, y, and z. We integrate over all possible locations where the reaction could have happened. And we integrate over all possible times at which the reaction could have happened. We calculate all that stuff. It gives us an amplitude. We calculate all that for the other possible way that the reaction occurred. That gives us a second amplitude. We add those two together mathematically. We square them. We get a probability that tells us how likely the reaction is to happen with products coming out in certain directions, and it works. This really works. Okay, here's some more pictures of, well, this is a picture of one of those particle detectors. So you can see the particle detectors are, where is the beamline in this? So these high energy particles come shooting out through these different materials. There's a bunch of electronics inside here, and so as the high energy particles come through, they're kind of like really high-end Geiger counters. And so these detectors are designed so that they can pick up particles as they fly by, and then we use, well, here's a computer screen representing what has happened during one of the events. So maybe a proton ran into an antiproton, and these are the particles that came through our detector. Okay, this is just a list of the particles that we work with in nature. Now, gravitation is the one that we don't have a model of gravity in terms of gravitons, at least not one that's mathematically consistent. So we can write down what we think are some of the properties of gravitons, but we don't have an actual set of mathematics that allows us to go in and predict different gravitational effects based on gravitons. What we do have is we have a description of the strong force in terms of quarks and gluons. And mathematically, this is really challenging to work with. So we can get, we can make predictions from this. And then we have a model of the electromagnetic force using photons. And that one, along with the weak force. So the electric and magnetic forces using photons, and then the weak force using W's and Z's, those we can carry out the calculations with extraordinary precision. And so far, everything that's been observed matches up exactly. And again, sometimes this is within a few parts, within a million of precision, where we're able to predict how these particle reactions occur and take place. Okay, now they're talking about antiparticles. I guess this is kind of after the fact. There's an anti-electron called a positron. It has the opposite charge, but it's more than just charge. So it's not just the charge that's reversed. It's kind of a whole set of properties that get reversed. Okay, this is something I guess we need to talk about. There are these tables in the chapter. I apologize for these. Or maybe not. I guess what I should say is you don't have to memorize these. That's not the intention of this chapter at all. Now, in this table, table 43.2, it does have a list of the fundamental force particles in nature. There they are. And then it has a list of the leptons, but it doesn't have the quarks. So here's all the leptons. So what you want to be able to do is just, you want to be able to look at the table and make some sense with these fundamental particles. And I would say just use the table patterns, the organizations that we've shown in the earlier slides. Now down here we have, well, what we said were mesons, quarks and antiquarks, and then baryons. Unfortunately, I don't feel like they have them listed as simply as they should be. They should just say what quarks make up which of these. I think that would be a much easier way to approach it. So I'm going to say, don't worry about these tables. Okay, I think, see if you can get through the homework problem for the most part, not necessarily working from some of those extraordinarily inclusive tables that they have. Here's what we've already talked about too. Here are quarks. I've got 3 quarks that make up a proton, 3 quarks that make up a neutron. I need 1 quark in each of the possible 3 states of red, green, and blue in order to give me an attractive force according to the strong force. For the proton, it's up, up, down, which gives us a net charge of +1. For the neutron, it's up, down, down, which gives us a net charge of 0. There are antiprotons and antineutrons, and those are made up of antiquarks. Here are the pions. So this is very similar to a diagram we already did. The pi plus, the pi minus, oh no, that's a kaon. So that's a strange quark instead of a down quark. Okay, once you start putting s quarks in, those particles get called kaons. All right, here is a list of the quarks: up, down, strange, charm, bottom, top. This is kind of interesting. Look at those masses. In terms of MeV, the ups and downs are really, really low mass. So if I look at those masses, what makes up most of the mass of a proton or a neutron? And it's not the quarks. The quarks do not make up the majority of the mass. It's all of the gluons and all of the interactions that are taking place. So protons and neutrons, most of their mass is coming from the gluons reacting with the quarks, and then sets of quarks and antiquarks that are being produced in those fields. So that's kind of a turnaround to where now mass is not the major effect going on. It's actually the energy of the color fields that provide most of the mass of those particles. All right, and then they talk about strangeness and charmness and bottomness and topness. All we're going to do is just talk about flavors. So flavors, I think, is an easier way. But again, the interesting feature here I think you want to take away is look at the top quark, mass 173,000 MeV compared with 2 MeV for an up quark. Okay, here are some examples of mesons. These are quark, antiquark, and these are examples of baryons. Again, what they should really do is just tell you what quarks they're made out of. These are examples of mesons and baryons that include charmed quarks and bottom quarks. So again, don't worry about all these tables and all these long lists. Now there are what are called grand unified theories. What researchers have wondered about is it possible to take the electric and magnetic forces, combine them with the weak force, and then maybe even combine them with the strong force? So currently what happens is that we have a separate force constant for each one of the forces. So the electric and magnetic force has its own force constant. We've seen that, the little k that we introduced. There is a constant for the weak force, and there's a constant for the strong force. Now, researchers, theorists have shown that the electric and the weak force actually kind of overlap in a sense. They kind of share some of the same features among the force constant. It's not a complete unification, but it's a partial unification between those two forces of nature. So again, there's been this speculation that maybe there's a set of interactions that we have not observed yet that will show that all of these can be unified. Now, another issue that comes up that we had mentioned earlier, is there a way to bring gravity into all of this? Is gravity going to be understood in terms of gravitons, in terms of some kind of a fundamental particle, or is gravity always going to be kind of its own force, separate from what we've been describing here in this chapter. Okay, I think that's it. I think we are through. So again, what I'm going to suggest is don't get too caught up with the long list of particles in these tables. I'm going to say if we can go back and look at some of the examples that we had set up. So this was kind of our organization as to what particles exist. We went through some examples of some different reactions, and we wrote down some Feynman diagrams showing how those work. And then take a look at the homework problems that have been assigned. Whatever questions come up, stop by office hours and we can get those looked at. And I hope we can make some sense of this. I hope that it can be kind of fun to see what really is understood within particle physics, and then also see how much of what we do in this chapter is really based on a lot of the ideas that we have already looked at. All right, hope to see you guys in office hours with those questions.